the organizers. This is one of my favorite places in Brazil. It's really great to be here. Okay, so I'll talk about something that perhaps you're not very familiar with. So we'll try to motivate the reasoning behind this project and why it is interesting to carry it out. So this is my brief outline. So I'll go very quickly through the standard model cosmology and tensions, for then focusing on homogeneous cosmologies. So, I have another. So the standard model of cosmology is built upon some. Sorry. I need to press this, right? Okay. So, right. Okay. So standard model of cosmology is built up upon, at least at the moment, if you want, three main observables. And here they are, the CMB, supernovae, and BAO, which is just here summed up with the CMB. So you got in this famous plot the density of matter, the amount of matter in the universe. On the y-axis, the equation of state of dark energy, these unknown components that is accelerating the expansion of the universe. And all these three constraints, they all cross at a single spot, which is consistent with the standard model of cosmology, which is the lambda CDM model, with about 30% of matter, 70% of dark energy, and again, the equation of state close to -1, the one of the cosmological constant. On the right, you see the same kind of constraints, but just allowing for a time variation of the equation of state. And again, you see that, albeit with some big error bars, they all cross at the point of the regard that reflects the cosmological constant. So this is I stole this plot from this slide from Rocky Kolb. This is this very summary of our knowledge till now. So 95% is dark, and then you got a little gas, stars, neutrinos, and metals are really rare. So we are quite ignorant about the 95% of the content of the universe. So our main goals, we're summarizing very fast. We'd like to know the background evolution of the universe, question 1, and how perturbations grow, question 2. Okay? So at the moment, we know pretty well, we've seen that there are still big error bars on the evolution of the equation of state dark energy, but we're kind of confident about the background evolution. Perturbations, we are waiting for big experiments like the LSST, Euclid, JPAS, and so on. So summarizing, concordance model has a very good pros. It's a very good fit to a lot of data, simple and consistent. People are working out the phenomenology, including baryons, and so on. Problems, of course, are the dark matter and dark energy. And recently, there is some bad fit to some data, the so-called tension. So I'm just briefly going through the tensions now. For a comprehensive review, I point you to this nice work by Leandros and Scara. So you got, and this is not comprehensive. You find basically all tensions and anomalies in this review. Here I'm highlighting just a few, like perhaps the most well-known. So you got CMB anomalies. There is the cold spot. So it's a region that is very cold. And it's a fluctuation that CMB anomalies typically are around the 2-3 sigma level. Cold spot perhaps is one of the most prominent ones. And people have tried to look at it from any point of view. Could be a perturbation at the CMB time. Could be an anomalous structure on the line of sight from us to the CMB. Or could be just a statistical fluctuation. And if you do carefully, the statistics, it's all fine. Then you got this lensing amplitude tension correlated with the curvature, and here there have been a few papers following this issue. So basically, if you allow for this lengthening amplitude to be a free parameter, data tells you that this value is some 2-3 sigma ways from the value that should have in the standard model. And then perhaps the oldest and most interesting, at least for me, the hemispherical asymmetry. So if you look at the CMB with the dipole, including in the modeling some dipole modulation, you find a signature for this or dipole or hemispherical asymmetry. So one part of the sky is different from the other. And I find this very interesting because it could signal a small, right, but significant deviation from just large-scale isotropy and homogeneity. Then you got this large-scale dipole anisotropies. This has been discussed quite a lot during the last 2 years, especially given the papers by Sekrest and collaborators, including Subi Sarkar. So this is a very, I think it's called Baldwin and Ellis test. It was cooked up in the 70s, 80s, back when there were not really observations in cosmology. And so the idea is that if the metric is really FRW, if homogeneity and isotropy are true in the universe, then there should be a common reference frame in the universe, right? So that should coincide with our motion with respect to the CMB. So our motion with the CMB should allow us to take out our peculiar velocity and find this reference frame. And if you look at dipoles other than in the CMB, say in matter, at redshift, say 2, 3, so at distances which are much closer to us than the CMB scattered surface, then we should find that by subtracting all these dipoles, we find the same reference frame, because the FRW metric is just 1. So what they found is that instead is a different signal that is in disagreement with the dipole from the CMB at the level of 5 sigma. Okay? So this is a potentially very high significance tension. And to my understanding, nobody's really working on modeling this yet, because it's not easy to model. They call this so-called a tilted universe, so a universe that features very large-scale flows. And so at the moment, people are, I think, focusing mostly on data. And I'm still waiting for some independent analysis of the data, which is all public and available in GitHub, to see which issues there are with this analysis, because 5 sigma is Then changing completely topic, there's this small-scale CDM problems. So used to be the missing satellites, but now they're finding a lot of satellites with the better measurements. And now it's more the too big to fail problem. So it's basically due to how much baryons and dark matter and how many baryonic activity you expect in a given halo. So there's been mismatch, but this could be a poor understanding of baryons, or well, could be a problem of cold dark matter. Perhaps dark matter is not that simple idea that we have of it. Then, more on the cosmological side, we have the high versus low redshift tension on the sigma 8 omega matter plane. And this has been highlighted by different observables, so by cluster counts, by weak lensing, and perhaps Jesse will talk a little bit about this later. And of course, this is not a severe tension at all. It's like 2 sigma level. Well, it depends on what the observer you look at. But surely will be what everybody is waiting for when new data will come, right? Because this is really represents a mismatch between what you expect from the CMB fluctuations and what you observe at the late times. And the same actually happens with the tension on H0. Again, it's the mismatch between what you expect to measure given CMB and what you measure at all redshifts. And this, nowadays, I think it is the tension in the standard model and reached 5 sigma last December. Okay? However, I think this is really important, especially for CMB anomalies, because CMB, you got a lot of data points. So you can find anomalies for sure, by definition. So bear in mind that the Lucas-over effect, which means it's difficult to assess these anomalies because nobody published in the journal of failed tests, right? So you keep looking, find nothing, you publish nothing. However, the journals we published they are journals of outliers. So basically, all the anomalies, they suffer from significance inflation. This is for sure. How significant is significant inflation has to be assessed. In particle physics, there is a well-known procedure for doing that because you got your accelerator in front of you. Cosmology is more difficult. Okay, so this talk is about inhomogeneous cosmologies. First, what are inhomogeneous cosmologies? So this is the study of the universe without assuming a priori an FRW metric, that is homogeneity and isotropy on large scales. And well, these are three basic motivations. First is to test basic assumptions given our ignorance. Second is just a program to reconstruct a metric from observations. So this is it is possible. Of course, you cannot be totally free. You need to introduce a modeling and constrain your modeling. But it is possible to constrain to some degrees, some metric degrees of freedom direct from observation rather than a priori constrain them. Lastly, and recently, we have these tensions, especially for this field. This knot tension is potentially interesting. However, it showed that in homogeneous cosmology cannot solve this knot tension. This is a spoiler. And then even more for me, cosmic dipoles and anisotropy. Okay. So in homogeneous cosmology, it's too difficult a topic given like that. Okay. How can you do cosmology without defining a background metric? So then one can introduce a subset of it, which I call the early FRW cosmology. So it's an arbitrary inhomogeneous cosmology. Well, the first assumption, is to say that, of course, we want to be Copernican, right? Because we cannot admit that we are really special in such a big universe. So the basic idea is that the Copernican principle is valid on a grander scale. Not just a standard 100 megaparsec, maybe it's a gigaparsec, 10 gigaparsec, whatever, but will be valid at some point on larger scales. Second, these early FRW cosmologies are cosmology which features, so imagine lambda CDM. You put on top some, You put on top some extra stuff. The requirement is that this extra stuff goes away at early times. Okay? So they're all basically decaying modes. Sorry, growing modes towards present time. So you can think of it as a kind of very weird primordial non-Gaussianity with correlated phases and stuff. Okay? And so this requirement is also something practical, because if you do so, then you can use existing codes, such as gadget or GR codes like Ramsey's concept, etc. Without this subset of cosmology, you're really lost. You don't know how to simulate the universe. Especially don't know how to include then the CMB in your likelihood, which is essential to do present cosmology. Okay? So this is the first slide, and I'll come back to this point. But so this is the first line of a series of possibilities for modeling the homogeneous universe. The subject of this talk will be regarding this modeling, which is the step one. So here we are us, the ICTP, and the space-time is modeled as a Lemaitre-Bondi metric, which is spherically homogeneous and isotropic, so it's just a ball, which is embedded into FRW. So at this circle, you go back to FRW exactly. Okay, so it's a large-scale perturbation, spherically symmetric. Justification is this one. so-called spherical cow. It was, I think, invented back in the States half a century ago. So it's the way physics work. We want to simplify as much as possible. So this is the first step. So I'm not saying this is a good approximation. It's the first step. So and this is then what I call the lambda LTB model, which is lambda CDM endowed with a spherical under or over density. Okay? Second approximation, and this is worse. Where is the observer? At the center. Okay? So these are two separate things. How you model space-time, where you place the observer. So at the center, justification. Well, if this structure is nonlinear, it's a good approximation. Because a posteriori, we know that CMB constrains the observer at the dead center of the structure. Otherwise, there would be a huge dipole in the CMB, and this cannot be, right? So if nonlinear, this is good. If, however, the structure turns out to be linear, then the approximation is not so good. Basically, you're saying that you're averaging observation over angles. You're neglecting anisotropic degrees of freedom. And at the end of the day, what happens is that anisotropies are as important and radial in homogeneity, so the modeling is not as satisfactory. So this next step would be indeed to move the observer from the center. But for this talk, the observer will be at the center. Again, due to manpower limitations. So what is LTB? A quick slide to summarize it. So here, using a trick. So I'm hiding everything under the carpet, all the dust. Why? So this looks very much like FRW because the weight is written, but it's more complex, of course. So you see, it's just FRW, but things get subscripts and R dependencies. So in FRW, you got these two scale factors are the same. The curvature is a constant. Here is a function. Because of these two different scale factors, you have two different Hubble scales, Hubble rates. And this means that you distort, for example, BAO in different ways, along the line of sight or perpendicular to it. The Friedman equation becomes something like that. Again, I'm hiding everything in a smart way. So this is it's not really the matter density. This is the integrated matter up to that shell, excluding using a Euclidean volume integral anyway. But I mean, this is when you go to LTB, you generalize your matter in this way. Cosmological constant remains the same, and then the curvature gets an R dependence. You can also write it as a function of R-dependent density parameters. So this metric is defined by a set of functions. Some are gauge, so they are not interesting. The physical ones are curvature, which give you growing modes. Okay, so you perturb the curvature, you have a growing mode in your solution. And then you got the Bank time. So you can decide when the universe started. Okay? And this gives you decay modes. So as I said before, I want to only study early FRW cosmology. So in this case, you need to kill the decay modes. So you put a homogeneous Bank time. Okay? So the only free parameter here is the curvature function, which we model in this way. This is a way to match the metric at a finite radius. And the only free parameters here are the background curvature, which we're going to use flat most of the analysis, and the curvature at the center, which defines if there is a center over density or under density. So here to give you an example, I'm done with time. So we got here the radial coordinate. So this is, imagine this as an FRW coordinate, like a simulation box coordinate, and not a gauge coordinate. So this is just your box. And this is your density profile. And this is the integrated profile. So in order to have a matching at a finite radius, you need to compensate the underdensity with the overdense shell, and vice versa. And so you see the kind of fluctuation, the density parameters. The density parameter is lower here. You got curvature, etc. And here I'm showing the Hubble rate. So you see that locally you have a higher Hubble rate than globally. Okay? And then where you have when you have this big...
just fix your mic because
it's weird.
Where's the mic?
I don't know.
That's the problem.
Okay, well...
Let's see if it's better now.
Okay, better? Okay. So you see, an interesting point that will be relevant for for later is this departure here. You see, when you got spatial gradients, so in a homogeneous metric, it's categorized by what? By spatial gradients, because if it's homogeneous, you go back to FRW. So when you have the spatial gradients, you have a big difference between the two Hubble rates. Okay? So this is a trademark for homogeneous cosmologies.
I have a real question now. What's the difference between the small delta and the capital delta?
So delta is the local density contrast.
People ask without the microphone, please repeat the question. No, you can repeat the question.
Yes. Okay. So Rogerio was asking what is the difference between small delta and big delta. So small delta is the local density contrast. Big delta is the integrated density contrast. So take into account all the matter from the origin to a given shell. So this is why it never, you see, what matters for the matching, for the Israel boundary condition, is the integrated contrast. And it has to reach exactly the FRW value to have the matching. Okay? So again, you have a compensating shell if you have, no, compensating overdensity if you have an inner underdensity.
So the matching is at 2000? Right?
Exactly. At 2000, you are in FRW locally.
Both go to...
Yes, both go, but by construction. But you know, here you're at FRW value. But there, you're not in FRW. Okay? So naively, you say, you got a solution for the Hubble tension, right? Look at here. This is 73, right? So in principle, you can easily, you put some whatever structure, and you fix the Hubble tension.
Valerio, just one more question. Sorry. We do have a physical overdensity near 2000, the blue one. Is this physical?
Yes, exactly. It's physical. So you have. So again, the other question was if this is a physical overdensity, and it is yes. You got the idea you have an underdensity, and then a higher density shell, and then FRW. Vice versa, I'll show another plot later. You can have an overdensity, then a surrounding void, and then FRW. Okay. Here giving the equations for the Newtonian potential, which is given as a function of these curvature functions. And these are how the luminosity distance and Hubble rate change on the light cone. Okay? But again, let's look at this Hubble tension thing. Sorry, no, first I need to discuss the Copernican prior. So okay, you're free to include this in homogeneity, right? But is it allowed by standard cosmology? To do that, we need to build a statistical measure for that. And the idea is to let observations constrain this arbitrary homogeneous metric, that is the parameter RB and ZB, which be the size and KC or delta 0, which be and the contrast of the homogeneity, that is how big and deep it is. So observation will constrain that. Our expectation will be given by the standard power spectrum as constrained by the CMB. Why? Because if the universe is FRW, right, this fluctuation at CMB time should also be here. So the same physics, same fluctuation should be present at these different places in the universe, because the universe is homogeneous and isotropic. So this Copernican prior is built in the following way. So sigma is just the root mean square fluctuations on a given scale, just the mass fluctuations. Delta is instead the size of the inhomogeneity, right? So this prior depends on, again, those parameters that I told you before, the size of the structure and its contrast. And this tells you how many sigma away you are given that scale and depth from standard cosmology, given the parameters from the CMB, which are convolved via their likelihood. Okay? So this prior simply tells you, no, if standard cosmology is true, that this is the distribution of possible contrast and sizes. Okay? Observables, we use CMB, latest, well, the Pantheon or the Pantheon Plus. Pantheon Plus is more recent. Then we split supernova between old data and just a low-redshift sample that is used to fit H0. Cosmic chronometers, BAO, compactwise distortion, kinetic noise Zeldovich, and also local calibration for the luminosity absolute magneton from shoes. Okay, so basically all data that we have, except perturbation data. So regarding the local calibration, just very quickly, so determination of H0 by shoes is a two-step process. First, you need to build your ladders to constrain the luminosity of the supernova. Second, you use Hubble flow supernovae to constrain H0. Okay? You want to do that model independently, so people have been using cosmography to do so. And with the detail that shoes collaboration adopts a cosmography with fixed values of the acceleration parameter and jerk parameters, which are justified because these are the values that correspond to standard cosmology. So it's a bit circular. So this means that the determination of H0 by the shoes collaboration does assume higher redshift measurement. Okay? So it's not really model independent. So we proposed that one actually should skip this second step altogether. No, you don't need to do that. Why? Because you can just do your cosmological inference with your favorite model by including a prior on the absolute magnitude of supernovae. In this way, you avoid double counting supernovae, you avoid using cosmography, even worse with the fixed values for its parameters. And also include further information analysis, the values of the calibration, because you're not free to, I mean, people have been doing cosmological inference in kind of a bipolar way, because you use H0, and H0 demands for calibration of the absolute magnitude of supernovae. Then you use supernovae with CMB, and you let MB with the flat prior. No, ignorance prior, but you're not ignorant. You do know the value of MB. And then CMB would push MB towards a value which is different from the one that is required for the H0 measurement. And this inconsistency usually is not accounted for in analysis. But if you do include a prior MB, this is correctly taken into account. And we show this, how this works with the hockey stick dark energy. So if you're interested, you can look at this paper. And we also, I mean, basic idea is just you don't put this chi-square in your analysis, you put this chi-square in your analysis. Just that, very simple. Okay? Anyway, nowadays also shoes collaboration acknowledges that, and they released for the first time the likelihood for the calibrations of the supernovae on the cosmic ladder supernovae. So you can download their Cosmosis code and include just a calibration on the supernovae, and then analyze it with your favorite cosmology. It could be F of R, DGP, interacting dark energy, you name it. Okay, well, it's just a parenthesis. Anyway, so going back to the main question. Can a local void solve this tension? First, can the standard cosmology solve this question? So in standard cosmology, you do have local voids. No, they are allowed. You know, it's not that it's forbidden. However, this is called cosmic variance, and it's given by just standard fluctuations. And turns out that it gives at most 1 kilometer per cycle per megaparsec, very generously at most. But you need 6. So no, this is not n. So standard cosmology cannot do that. What about an arbitrary inhomogeneity, right? The one beyond. So you need some mechanism to produce these anomalously large underdensities. So if you include CMB, full spectrum, right? The supernovae that Rees and Shoes use to constrain H0 in this range, and then the calibration on MB from Cepheid, then yes, you can. Local H0 It's compatible with CMB, with everything. The value is great. And then homogeneity that you need is far from what you expect from the standard model. So this is the Copernican prior, what you expect from standard cosmology. However, as soon as you add all supernovae, you go from red to black. So, and you go from, again, from this blue curve, sorry for the color that I inverted, from the blue to red. So basically, if you add all supernovae, you cannot anymore explain the Hubble tension. Data do not allow for a large underdensity nearby. As simple as that. Okay? The measurement of the luminosity distance are very accurate. So this is not a solution. Okay? This plot instead shows, focuses more on the constraints on the space-time, given all available observations, the one that I listed before. So again, CMB, supernovae, BAO, kinetic, Y distortion. And at the end of the day, you reach constraints that are given by these black contours, which are very similar to the one that you expect from a standard cosmology, okay, from the Copernican principle. So you could say that, all right, we confirm the Copernican principle, we confirm FRW, and so on. We also try to reconstruct the metric by allowing for a more general density profile. And the metric does exhibit a local underdensity, but it's too small to explain away the Hubble tension. And it's 2 sigma compatible with standard cosmology. So this is, if you want, the local reconstruction of our space-time. So you could use these results if you want to account for, to decrease the effect of cosmic variance on the position of the observer. Okay? However, there are, of course, this analysis just a first step, because the constraints are tight, but the setup is very simple, very simplified. It's not just the observer which is at the center, who is the center, but also the profile which is rigid, monotonic. For technical issues, you cannot do better than that. Okay? Second, constraints here comes only from background observables. But the real name of the game of the future is perturbation observables, growth of structures, LSST, Euclid, JPAS, you name it. So if you really want to make progress with the more general modeling, so you need more information, you need to account for the growth of structures. And this is why I started this BHOMO project, Cosmology Beyond Homogeneity and Isotropy. So the idea is to study numerically in homogeneous cosmology. Okay? So it is not possible well, you can write down the equations for the growth of perturbation in homogeneous background. It's very complicated. It's almost, people have tried to solve it numerically, but I didn't see a clear answer to how one can use that modeling for comparing with the observations. Okay? And however, one can tackle this problem with numerical simulations. Okay? The next steps, of course, would be a better modeling of homogeneity. But for the beginning, we started with, again, the lambda LTB model, the simplest possible early FRW cosmology, which, again, is a kind of an archetype of homogeneity in order to explore the effect of spatial gradients on the growth of perturbations. If you want to see more information, you can find them at this website. There's the big QR code there. So why can you actually do numerical cosmology? It's not trivial. So the lucky bit, at least for lambda LTB models, is that Newtonian codes can reproduce the evolution of a general relativistic metric such as LTB, even at larger scales. The reason is basically because of spherical symmetry, and because it's the matter component are just dust and cosmological constants. So you do not have neither sound waves or gravitational waves. So And thanks to this, this is a scalar invariant evolution, which can be described via Newtonian codes. Okay? So this is for more general model, this is not certain. One has to check this again, how accurate are Newtonian codes, such as gadget, to model in homogeneous cosmologies. Growth of perturbations. So because of mode coupling, basically you can think of this as a standard perturbation becomes second order, because you have a background in homogeneous background, which is your first order perturbation. On top of it, standard perturbation, which becomes second order. And then you have mode coupling. So it becomes a big mess, such that even linear perturbations, you don't really know how do they grow. So really, this is a unknown territory. And again, the goal of this BHOMO project is to understand and model this via the method of numerical cosmology. So at the moment, I've run a suite of 68 simulations. Every line is actually 13 simulations, more or less. Various boxes of different sizes. And for each box, you have various contrasts. All this data is available. Of course, the snapshots are not, you cannot just download them because being large, the transfer cannot be made available. But if you're interested, please contact me. And because I need manpower to analyze the snapshots, and you can do a lot of interesting physics with this. Okay, so please contact me. Cosmology is fixed to some, I remember, Planck plus DES cosmology, some concordance cosmology. And what is changing are only the inhomogeneous parameters. Okay? For each box, you also have a lambda CDM simulation to compare things. So here I'm showing how the background evolution is recovered within the simulation. So these are simulations that are run with no perturbations. So AS basically 0. And you see how the Newtonian simulation correctly describes the evolution, very nonlinear evolution, up to, given the scales, for any scale, any box. Okay? All right, initial conditions. Initial conditions, should be a GIF. So initial conditions are given in this way. So you just add to the standard potential given by your Gaussian perturbation, a standard potential given by your inhomogeneous perturbation. Okay? And then you feed these, so you use this Falcon IC code. Then the special initial conditions are just fed to a standard gadget. We use Open Gadget 3, but you can use any Gadget 4, any variations. Okay? Interestingly, we use the same lambda CDM seed. So this is nice because you maintain the large-scale structure. So you will see that in homogeneity will deform filaments and voids, right? Because we kept the same seed. This is really, so here you see the subtle change between one simulation and the other. Of course, all these plots are for exaggerated parameters in order to maximize the visual effect. So here, the distribution is good enough, I think. So here, these are 3 simulations from one of the smallest box 1, the smallest. So this is lambda CDM. This is central contrast, central under density. So you see, for example, this filament here is present in all of them. It gets distorted because of the background evolution, but also structures grow differently. You see that there is more structure here than here. Okay? So you want to model that, because background evolution, we know it. But we like to really know how perturbations evolve at these different positions. So this is the same plot, but just checking the radial profile if it agrees with the solution from GR. It's all good. This is the same stuff, but for a box 3, much larger box. So you can see the inhomogeneity better because you average more over smaller structures. At larger scale, everything gets more homogeneous. And these circles, they mark, this marks the matching to FRW. So everything beyond this point will be exactly the same. So this arrow is the same as this arrow and this one. Inside, instead, it will be the evolution. And this smaller circle marks the transition between underdensity and overdensity. Okay? And here, because it's a much larger box, you average cosmic variance over, and you agree very well with the GR solution. Here is a GIF. If it's working, yeah, it is. This is just going through the different simulation, changing delta Z, delta naught. Okay? You see, this is particularly interesting to see how the structure are maintained but weakened, because of the structure. You see how the distortion in the cosmic web. All right, so data products. So we got full snapshots for 12 snapshots, totally available. Only the even one are kept, but all the other ones were all used to produce halo catalogs from Rockstar. We got 40 properties, so fully characterizing the halos, and lens planes using slicers. And this is interesting because of the matching condition, boundary conditions, you can be light cone as you want. You can glue things, doing like a mosaic. Right? So you got a lambda CDM light cone, a light cone with a lot of structure in between, but you can also put just one structure anywhere you want. So for example, if you'd like to study, to have a model for the cold spot given by an intervening a structure that is in between us and the CMB, this would be like a very good modeling. Okay, so now let's go to the modeling. So at the background level, ЛLTB is silent. This is a name that was given by Mattarese, Bruni, and collaborators some time ago. However, at the perturbation level, we got that the magnetic wave tensor couples to scalar to tensor perturbation modes. And this is a big mess, becomes a nightmare. They've been grouped by Chris Clarkson, Bartelman, and also another one in Japan. They were trying to tackle this, but with no, I think, concluding results. So you got these 4 possibilities, full set of coupled equations, a nightmare, silent approximation, I will describe it now, local FRW approximation, or second order perturbation theory.
Question before you go on. So as you said, when you have a transition, you have to satisfy these radical juncture conditions. But that means there is a shell there with specific properties. So you have a fluid with some particular properties. Is that fluid sensible, and should be there in nature?
No, it's just dust and cosmological constant.
Can you repeat the question?
So, okay. So Luis was asking if given to the matching condition, you need to have some weird fluid to allow for that. Sometimes you can have discontinuities, this kind of stuff. But no, it's the matter content is just dust, cosmological constant, and just you modulate the density profile such that at a finite radius, you reach the values, the background values, and at that point
But I'm talking about the fluid on the shell as the transition takes place. So there is a discontinuity across that transition. So what are the properties of the fluid there?
on the shell, the transition on the shell in between ЛLTB and FRW. Okay, right. So we use the continuity is up to. So we use 3 times differentiable. So actually, it's continuous down to. No, we have continuity at all relevant orders. So there's nothing really going on. I mean, it's a smooth transition between an ЛLTB to FRW. Yeah. But we can discuss it later. Okay. So here I'm talking about the silent perturbation approach and the local FRW. So basically this is work by Zebin, 2008. He laid down all these equations. So you do a 1 + 1 + 2 decomposition, exploiting the symmetries of the LTB matrix, spherically symmetric. So you can write this. You can write these 4 scalars. So this is the local density, local expansion, shear, and this will be the electric wheel scalar. Okay. And then you can look at, so at the background level, it's all fine. Right? There is an analytic solution. Not really an analytic solution. If there is lambda, we need to do some, well, it's a bit more complicated, but you can have an almost analytical solution. At the linear level, you have this. Right? So you introduce your perturbation variables, and this is a set of equations. You give the initial condition at method-dominated area, etc. So you give initial conditions, you solve these equations, then you can build a set of transfer functions. So here X stands for these 4 scalars. And then you have these things basically transforms the initial values for these quantities into values at a given time, a given R. Okay? So these are LTB transfer functions. So you have the standard transfer function in cosmology that are there, of course, and these are what they transform those initial perturbations, because we assume that thanks to the metric being early FRW, that at early times you can do harmonic decomposition and everything. So you take those perturbations, and this transforms them into their values at the present time. Okay? So it's a very convenient way to model all this problem. Credit to James Zebin. Now, if this element here in the set of equations is negligible, right? Then basically you decouple density and expansion from the other two, especially from the more complicated ones, and you go back to standard cosmology. Okay? It's a standard cosmology, of course, with some specific parameters for this local Hubble rate and density parameter, which are not, these are like effective parameters. They are not realized locally, neither globally. But still, it's an equation that is trivial to solve. And then, it would be very interesting if you could model the growth of perturbation in LTB using such a symbol approach. Of course, this is true only if this term is subdominant. And you could compare it with for example, this term here, and make a ratio and check if this is much less than 1. So if you do that, so these are 2 examples of inhomogeneities. So this is central underdensity, this is a central overdensity. You see the matching is again at this dashed dotted line. The Hubble rate is higher here is lower than global, etc., etc. But you see that in this case, that is it's a large inhomogeneity, minus 0.4 and plus 0.4. This gamma, that should be much less than 1, actually is not much less than 1 in this case. It goes to minus 0.3 for the underdensity. For the overdensity, smaller. Why is that? This is because of intrinsic dynamics of LTB. And LTB eventually gives rise to shell crossing, because this central underdensity keep pushing. The background is fixed, because you got the matching. And what is in between gets squeezed till you reach shell crossing. That is, you have 2 shells the same point. And for this reason, underdensities that feature more larger spatial gradients than overdensities. So in this plot, the other way around, you look at the dependence of gamma at a fixed radii as a function of delta naught. So actually, you see that this local FRW approximation is not expected to hold in general, not at all. However, if deviation from homogeneity are within perhaps 10%, then it could work. But that has to be tested again, because this is just order of magnitude estimate. So clustering. So in FRW is the standard stuff. You have your power spectrum, you put it inside, You put your window function, in our case is constant, and you get your CL. In LTB, within the silent approximation, you need to beat a much more complicated transfer function here. You have the standard transfer function, so you have the LTB transfer function. It's a big mess. But in the local FRW approximation, the difference between LTB and FRW is just an overall factor. Just the power becomes different. Okay, so the modeling, in order to respect the symmetry, you have to model observables accordingly. Well, you can also take different points of view, but at least at the first step, we only look at angular quantities, because it doesn't really make sense to compute a 3D power spectrum if you do not have homogeneity and isotropy. You can do it if you look for a signal, and this is another project we have in mind. And we computed CLs using Hill peaks and W's, core func. And this is very preliminary. So these are Hill peaks maps from the simulations. And these are the CLs, and the modeling is working. Now we are applying to the lambda LTB. Preliminary because, again, we are limited by manpower. So if, again, someone is interested, please contact me. OK, so we have a list of many papers. So the paper 1 is already out. Paper 2 is a linear modeling. Paper 3, we like to do a path-like cone analysis, then looking on nonlinear perturbation, lensing, Hale abundances, biases. Hale abundances especially can be very interesting because you can look at the effects of secondary bias and stuff. Halo profile concentrations. And then, you can study dipole, bulk motions, and fractal dimensions, and you name it. There are many things you can do. Before concluding the very last minute, just a future perspective, my take on homogeneous cosmology. So I already talked about this. We are here at this moment. Second step is to allow for any size contrast and off-center displacement of the observer. So we would be here. Space-time will be still the same, still the spherical cow. But spherical cow is not too bad, actually, because voids do tend to get spherical, for example. And halos are modeled always as spherical halos. So why not, right? It's not necessarily terrible. So here, what we're working on this right now. We need to build an off-center ray tracing module, which is not trivial. And we expect important constraints from the CMB. So CMB actually is the main issues, I think, with having a generally inhomogeneous model, because there is little anisotropy that is allowed for by CMB. Another step could be you take the same LTB, and you just make thanks to the matching condition, you can put as many as you want. They cannot cross, of course. So this is not very precise because you got bubbles that cross in the Swiss cheese, but nevertheless, this is called the Swiss cheese model. You can place the observer as where you want. And this is a smart way to bypass the limitation of LTB. That is a fixed profile and size, then you put many, then you can change profile for every void. And the construction is quite trivial. The integration, the light co-integration, not so perhaps. Then you can go ahead and, OK, let's switch metric. Let's go to Saccharis, the next easy thing. Saccharis still has a matching at a spherical radius, but inside it features a dipole homogeneity, right? But again, the LTB is already a pain. Imagine Saccharis is like a long list of free functions. Is it really worth it? Why? So we've seen with LTB already, from the CMB itself, naively, we expect, we cannot have big departures. We are looking at percentage effects. So the idea in homogeneous cosmology, I think, is what if there is, at large scales, some percentage effect, some 0.03 contrast structure that could give you interesting signals, hemispherical isotropy, cosmic dipoles, etc. But for that structure, you don't really need a general relativistic solution, right? Because those are useful when you have no linear structures. And of course, being exact, you don't have to worry about convergence. But for nonlinear, but these are ruled out. And so I think that the next step really would be a perturbative approach. trying to find a smart way with not too many degrees of freedom to model the inhomogeneous universe. Of course, you need to test this with simulations, and not just, of course, at the end of the day, you want to run Newtonian simulations because those are cheap to run, very well tested, and can give stuff that you can use to compare with observations. But then you have also to test some lower resolution version with GR codes to make sure that you're not simulating something that doesn't make sense. Okay, because again, you are departing from FRW at gigapart scales, perhaps. So, well, this is the program that I started, and well, many years to come to reach this level, but that's all. Thank you.
So questions? Yes, many questions. That's great. So first, go here, then I do have time to go there. Sorry.
So thank you for the talk. The LTB metric is spherically symmetric, right?
Yeah.
You have a center.
Yeah.
And isn't this a special point? How do you conciliate this with the Copernican principle?
Yeah, so this is indeed the very problem of this first setup. So there are two separate issues. The modeling of the space-time. So when you model the space-time LTB, the observer is not there yet, so there is not problem for an observer. So no, that's the spherical cow problem. Okay, so you need to think if a 1 gigaparsec structure, spherically symmetric, makes sense or not. Probably it's a very spherical cow problem, so probably it does not really. Second problem is the observer, and you're correct. If you're at the center, it's a gross violation of the Copernican principle. Indeed, these are called non-Copernican principle. It is non-Copernican, where the so-called non-Copernican alternative to dark energy. So back in the day, people were really trying to explain away dark energy with this. The simple idea is that you can change your light cone. So faster expansion now than yesterday becomes faster expansion here than there. No, you have total degeneracy. You can reproduce with LTB any luminosity distance function. Totally. Okay. So, but these models were ruled out, right? They produce too much kinetics and Dodge effect because you have insanely large velocities going outwards, and so matter will interact with CMB, and we give you signals that are ruled out by zillions of sigmas. This was a famous paper by Zhang and Stebbins, and later by Zibin also. So we are not trying to. So we're not the center of a void. We're the center of a homogeneous structure of any contrast. So if this structure is nonlinear, yeah, if it's nonlinear, then you really need to be at the center. Because in that case of the center, so you need to be within 20 megaparsec of the center, 50 megaparsec. Otherwise, you would have a too large dipole with respect to the CMB, and then you basically, I mean, you could hope for some cancellation, for peculiar motions, for due to your peculiar velocity, but this will be only one soldation. But in that case, if it's nonlinear, you're really explicitly violating the Copernican principle. So you're testing the Copernican principle. That is fine. I mean, if you're testing it, you build a model that is non-Copernican to exclude it. Okay? So this is fine. And we did this because I cannot go too much, but when those plots with the contours, you would see that the black contours would match the expectation in green. So you cannot have large structures, a deep structure at a large radii. So this worked, this assumption was okay to be falsified. But now when you want to constrain the local space-time, then you're at a very nonlinear scale, very linear scale, like a few percentage of contrast. And at that point, yeah, it becomes a problem of modeling because you are placing, again, at the center without really a motivation because you don't want to falsify Copernican principle anymore. It is just a lack of modeling. So to solve that, you need to, at that point, really let the observer the distance has to be a free parameter in your MCMC chain, right? So at the moment we have lambda CDM, all the parameters plus radius and depth. Now we want to also add the distance of the observer from the center. And then you let the data tell you what it is.
Thank you.
So sorry, I go first on this side and then on the other side, so that I don't have to go back and forth.
So a little bit in line with what Sean said. Since you fix the observer and you're measuring all the quantities at the observer since you're receiving the signals, wouldn't that kind of violate gauge invariance? Because, for instance, in Robertson-Walker, and sometimes when you want to measure some effect from CMB, you change gauges because it's easier to follow the light rays. So how can you link the perturbations in limited N-body to the perturbations in lambda CDM if you're not, if you don't know exactly what the gauge you're using, and since you already postulated an observer, you can't change gauges because, well, you're already assuming a gauge.
So let me see. So at the background level, so all the constraints, so the observer here was the center only for background observables first, because that's what we can do at the moment. We cannot compare with the gross of structure yet. So for the background, you have this metric. You can read the luminosity distance directly from it. And then the gauge here is given by you are free to define your R coordinate. Right? You can change it as you want. And but the luminosity distance, once you define it, is it's a gauge independent. It's your observable. You solve the equations, and I mean for all the background observables, you can solve them in this way. So that's fine. For perturbations, then this R coordinate is something that is tricky and has to be taken into account. So you cannot so the equation that I gave you here, and here, no, here there is not an observer yet, right? In this, where is it? Yeah. So here it is this R coordinate, because to solve this equation, you have to you use the metric coordinate. But then when you compare to the simulation lives in your N-body gauge, right? So at first order, this is the same as this chi coordinate that is defined in a way, but it's the one that matters from the simulation. So you should be careful in using the correct coordinates, and that's not trivial issue, actually. I was working on this in these last months, how to correctly account for this.
Yeah, because I mean, since you're observing from the center of the homogeneity, it seems to me that when you go to the perturbed level, you can't change gauges that easily as you can, for instance, when you assume conformal Newtonian gauge and you already say these are the gauge invariant perturbations, right? How do you define these in LTB?
You can no, you can, if you can still, when you give initial conditions, where is it? No. Where is it? Here. Yeah. Mm-hmm. So oh, okay, this is a linear level.
Maybe we can discuss that later.
I mean, you should imagine this at a simulation level as just another perturbation on top of what you have. Because in simulation space, it is FRW. It's not LTB, it's FRW. The box evolves like according to FRW, all the particles, blah, blah, blah. just a perturbation, which luckily, its background evolution follows the GR solution because this GR solution is very constrained, it's very symmetric, dust, etc., scaling variance, all that. But yeah, but that's like kind of a coincidence. You could, so if you look at just as another perturbation, then basically you can apply the same.
Okay, thank you.
I don't know if I was clear.
Hi, thank you for the talk. Do you have any thoughts, or what would be the challenge for LSST data products related to inhomogeneous model, or any thoughts on that, or challenge how to calibrate something?
Yeah. That, of course, with the LSST will be, if you want to explore, because this is really interesting only if you explore large scale, very large scale homogeneity. So you want deep surveys. So LSST is deep, and for sure you can will be very useful to, once we have a theory, modeling for the cross structure, it will be very useful to constrain that. Now, all the calibration work tools will be done for lambda CDM. But again, it will be very small departures from lambda CDM. Perhaps smaller than modified gravity models. Perhaps will be more conservative this than, will be, so perhaps you could trust more, enough the data products to be applied to this kind of analysis. But regarding future data, what I'm even more excited than LSST, I'm sorry, but is dark science. Because with dark science, you go much deeper. So if you manage to use them for cosmology, there really you can constrain super large structures. Because basically you see all the events up to when we first start having coalescences. So that's big. But LSST will be surely, because it's deep. In Euclid, of course, also. There's,
So Valerio is a member of LSST. He forgot to mention.
Yeah.
So you can propose a project for this.
So thanks for the nice talk, Valerio. So yeah, actually, I had a question that you already answered before, but if I can, it's more out of curiosity. I saw that you mentioned about also anisotropic cosmologies, probably. You actually mentioned Bianchi cosmologies at some point. I just was wondering if you're planning also to explore these kind of things, or
Yeah. So that's a common one. Even Planck tested some that weird Bianchi with also with the spin. The thing is that you need to give initial conditions at early times. So at early times they have to become really FRW. And Bianchi, being homogeneous and anisotropic, so I have made that. So I was thinking about how to, if it's really possible. I didn't think very hard actually about that. But if you, because I never played with Bianchi, but if you have if you have played with them, you have some ideas, because it's a very practical issue. You need to have a CMB code to generate initial conditions. And that you need a model that satisfies that. Otherwise, you cannot simulate, you cannot do cosmology. Of course, you can imagine, okay, let's build a CMB code for inhomogeneous. Who can do that? I mean, you need it's not trivial, right? But it's a good question. I haven't looked at it really. I just thought about it.
So any more questions from this side before I go to the other side? Okay. I think Jesse has a question, right?
Hey. So in this scenario where you end up having like an overdense or an underdense shell at some distance, it seems like it'd show up in peculiar velocities, and naively, it seems like maybe studying the impact of that on like the apparent linear growth rate might be simpler than modeling the whole power spectrum. Have you looked at how RSD constraints on like F sigma 8 at different redshifts whether that can constrain this?
So, let me think. So, okay, so let's go to one of these pictures. Just to get the, where is it? Here. So, yeah, so you got, for example, another density, then you got the, then you imagine being the light cone, right? So you're the center. So so he, and then you look out, and then yes. So eventually, yes. So once you have a model. Again, you need a model for the growth of perturbation to compare with to see how F sigma 8 could change yeah, that's interesting because giving this modulation, you could have a degree of freedom to explain some and other parts and the different redshifts. Yeah, that eventually, yes, we'll do that. Yeah.
Yeah, and I can mention it maybe in my talk or later, but we looked at this model with like bin sigma and redshift, and one of the things we ran into that we had to figure out how to handle was if you like arbitrarily change the density in different redshift ranges, that'll give you implications for matter flowing from one shell to another.
Ah, interesting. Yeah, and anyway, this profile modeling, again, is people have been trying to work with a more general profile, so you can imagine some nodes of a spline, and then have some freedom in modeling. But again, I wouldn't do that with ΛLTB because ΛLTB, if you get into shell crossing very easily. I think, and it's not worth it because if it's linear, anyway, you can just do some perturbation stuff.
Since you are at this slide, regarding these compensated profiles, it looks like, for me, it's like you have a fine-tuned model because you really need that profile to average at 0 to have Friedman-Robertson-Walker after some scale, right? How difficult would be to implement a profile that you get FRW asymptotically?
Okay, so originally people were doing asymptotically, indeed, because well, it could seem more natural, but then it's dangerous because if you do MCMC with this model which can have arbitrarily large radii asymptotically, you could touch the CMB, right? So when you are at the CMB, you want to be FRW exactly. Otherwise, you can introduce biases and issues. So, and actually, it's not really fine-tuning because you see, you should look at it from the curvature function point of view. It's just that the curvature function goes to 0 at some finite radius. So instead of, so got your R, oh, these are big, okay, and well, just put here that is more visible. But instead of, you can do this, or you can do with a hyperbolic tangent and going to infinity. For many things could be equivalent, right? But so the issue is here that you need to ensure the derivability for the metric function, Christoffel symbol, everything to be fine. But this is just a technical issue. But doing this is much safer because, yeah, for many technical things, for example, how you define, essentially the main motivation is to avoid to be in FRW at the CMB time. I'd say redshift larger than 10, to be sure. Because hypergolic tangent is not, if you let the parameters free, you never know. Yeah. So it's really, once you ask for that, automatically you have a compensated shell.
Yeah.
Because what enters the dynamic is only the capital delta. So it's delta that matches. So it's a side effect that comes in a compensating shell.
Okay, any further questions? I'm not sure if Ricardo Sturani is looking at the YouTube channel to see if there is any online questions. But, so I have a curiosity question. You mentioned Sarkar's and collaborators' work in the beginning, and there are some claims that they have detected some anisotropy or some homogeneity, no? From Sarkar's group.
Yeah, so they looked at quasar.
Yes, and it doesn't agree with the direction of the dipole.
Exactly, so they found, I don't have a slide here, but so they found looking at the fluxes, so there is a way to parameterize the effect of a peculiar velocity with respect to the quasars, and they find a phi sigma signal. So
but you claim here that there's no, you looked at this and you didn't find anything, right?
Sorry?
You looked at this effect, not on this particular observable, but other observables, and you didn't find any sign of an isotropy or anything, or maybe I misunderstood.
No, Sarkar, the others,
yes.
you mean? So they found that the alignment of this quasar dipole is consistent, I think, with the CMB, more or less. But the amplitude is different. That's agreed at phi sigma.
Okay.
And then also they compare it with other anomalies. So you have the quadrupole, octupole, the axis of evil, and they were not much significant. I think that basically the thing is looks like the matter frame and the same frame are different.
Okay.
And with the tilt, with the flow, which is consistent in the direction.
Okay. Can that be fit in an LTB model or?
So you could, yeah. If you have a huge LTB and the CMB is within, so actually I'm working with that on that with some collaboration, Miguel Quartin, Notário da Bicamarena. We're trying to see what to do there. But yeah, it's not clear yet.
Okay. So Ricardo, no questions from, okay. Okay, so I don't see any hands up. So let's thank again Valerio for this very
Thank you.
So we break for lunch. I think there's some maybe suggestions in the package of lunches. If not, just follow a local person. There's several nearby places, per kilo places. What? Sorry.
We start back at 2.
Oh, we start at 2, yes.